Good morning, friends and dear students. I welcome you all here for my course, Engineering Thermodynamics. Till now, I have covered basic concept of thermodynamics like systems, surrounding, boundary, definition of properties, state, heat and work. In heat and work, in my last class, I have done one or two problems. Today, I am in the second problem solving exercise, which is heat and work part 2. As of now, we know that the thermodynamics we deals with heat and the work, and how this energy can be converted from heat to work or work to heat. This we have already discussed and we have seen. Today we will be discussing the second two problems, and these are the contents for this today's problem. That is numerical problem based problem related to work, PV diagram and its importance, hypothetical problems, and the real problems. This we will be discussing in today's class. So this is the second problem which I am going to discuss, and this is taken from reference 1. The refrigerant R22 is contained in a piston cylinder as shown in the figure below, where the volume is 11 liters when the piston hits the stop. The initial state is minus 30 degrees centigrade, 150 kilopascal with a volume of 10 liters. This system is brought indoors and warms up to 15 degrees centigrade. So here we can see that something hypothetical things are also given. So we have to find out that is the piston at the stop in the final state. So in the final state, whether this piston is here or not. If it is touching, then we can say that this piston is touching the stop. Okay, these are the stops here. This is the piston, and this is the system, and this system is R22 and its volume is given. So this is the control mass system where mass is not transferred, only energy transfer take place. So here we have to first find out that whether the piston is hitting this stop or not. So these are the stop. And second, how much work done is performed by this system. So this is our problem statement. So here the refrigerant R22 is contained. So this is here R22, which is mentioned in a piston cylinder as shown in the figure below, where the volume is 11 liter. So the volume of this thing is 11 liter when the piston hits the stop. So means when the piston is here, it is here, this total volume is here is given 11 liters. Hits the stop. The initial state is minus 30 degrees centigrade and 150 kilopascal with a volume of 10 liters. So initial condition is fully given, and the final is also given. The volume is given 11 liters. So this system is brought indoor and warms up to 15 degrees centigrade, and the final temperature is also given as a 15 degrees centigrade. So this is the problem. Let's see how we can go about. So first we have to draw this diagram. This is the piston cylinder diagram, and for this type of problem we have to draw the PV diagram. Without drawing the PV diagram, you will see here that the problem is going to be quite complex in nature. So PV diagram is very much essential. So this is the stop, this is the cylinder, and this is the here the piston. So we have to see that these all things are met. So here we can see that as per the problem, the given condition is V stop when the piston is reaching to here. This is the stop. This V stop is given 11 liters. So 11 into 10 to the power minus 3 meter cube, because we have to convert this liter into meter cube. Now state 1, the T1 is given minus 30 degrees centigrade, and the V1 is given 10 liter. It is 10 into 10 to the power minus 3 meter cube. So first state 1 is given. This is the state 1, and this state 1 is minus 30 degrees centigrade, and the volume of this is V1. So here this, we can say this is the V1, and here this temperature is minus 30 degrees centigrade. So here we can see that for this temperature, if we tempted to use ideal gas equation, that is P1 V1 by T1, because P1 V1 by T1 is equal to P2 V2 by T2, or we can write that P1 V1 is equal to M R T1. So here T1 is given, V1 is given, M is given, R is known, and so we can find out the P1, but we cannot use. Can we use this equation? No. Ideal gas equation we cannot use, as the ideal conditions are not existing. This R22 is not the ideal gas. It is a liquid, or there's some refrigerant. So this we cannot use. So we can use this equation. The answer is no, because this is a phase changing substance. This R22, the substance is R22, and this will very easily, it will change the phase from liquid to vapor, vapor to liquid as per the condition. So we cannot use the ideal gas equations which is mentioned here. These are the ideal gas equation we cannot use. We cannot use ideal gas equation as R22 is a refrigerant. So we need to use a table called R22 table. So R22 tables are available in every thermodynamic book, or we can have a separate steam table books. In that, these all things are available. By table we can get the specific volume V1 at state 1, that is V1. So from the table with P1 and T1 which are given, we can find the mass M is equal to V1 by V. V1, capital V1 by V. So here capital V1 is a total volume at state 1, which is given here, that V1 is already given, and at a specific volume at the state 1. So by this we can get the mass of the substance in the trapped part. Now let us assume piston hits. Now we are assuming that by the expansion of this it is hitting. So if hits the stop, then what will be the specific volume at state 2 and pressure 2? So V2 and P2. So if this is the state here 2, so what is the V2 and what is the T2? This we have to. So here additional data given at state 2 to identify the state point T2 is equal to 15 degrees centigrade. It is given. So it is true if verification shows that, then only state is real or hypothetical. Need to work out to assess the real point. So whether at the point 2 from here to here, whether it is hitting or not, that we have to find out, and that we have to see that whether it is hitting or not. So first we have to verify. So how we can verify this, we will see in the next slide. So here we can see that the V2 and T2 combination for R22 table will give the pressure P2. So with the V2 and with the temperature T2, this V2 is given because we know the mass. So this V2 is equal to V1 by mass. So this V2 we can get it. V1 is given. Mass we have just now find out. So after getting pressure P2, what to do with this pressure? So what we have to do? Suppose I am drawing here. This is the state. These are the stop here. So we have got now P2. We got the P2 from the table, and this P2 we have got 164.7 kilopascal, and P1 is already given as a 150 kilopascal. So why it is hit or not, that I want to see here. Here we have R22. Okay. So till the time the pressure here is 150 kilopascal, this pressure will try to make up to here. The same pressure, just about to touch. It is not touched, just about to touch. The same pressure will be maintaining 100 kilopascal. But as and when it hit, the volume will remain constant, and in the constant volume, pressure will increase. It means it is really hit. So that is the question which is asked, whether it is hitting or not. So the answer is yes. The answer is because this P2 which we have got from the table, we got 164.7 kilopascal, and this P2 is greater than the P1. Had P2 is less than P1, if this P2 is less than P1, assume it is 140 kilopascal, it will not hit. Or if it is 150 kilopascal also, it will not hit. To have the hit the piston, so if you assume it is the piston is moving, so it will have the same pressure as 150 till the time it is touching the stop. As it is touching this thing, and slowly this pressure is building up because the stops are there. So in the constant volume, the pressure will increase. So that is here indicate that at P2 we have 164.7 kilopascal, which is more than the initial condition which is present in the piston and cylinder here. These are the refrigerant. So it is slowly it is moving. Volume is increasing, but pressure will remain constant till the time it is just about to touch. As and when it is about to touch, the pressure will increase. So here we got the P2 is more than the 150 kilopascal, which is the initial condition. So it indicates that the piston has hit the stop. That is why the pressure is increasing. So P2 is greater than P1. So P2 is 164.7, which we have got from the table. Okay, understand that at the, we know the V2 and T2, from there we can find out this thing. This is given already. So from here we can find that this pressure is higher than the initial pressure. It means piston has hit the stop. And this is the answer of the first question, which is mentioned here. What will happen after hit? So what will happen after hit? The volume will not change, but pressure will build up as stop preventing to go up. Now we need to find out work done by this process. So we have to very much cautious that the work done is equal to PdV. So here what P we have to take and what the volume changes are there. This we have to ensure, because here we have 150 kilopascal, which is up to the stop. But after touching the stop, the pressure is increased to 164.7. So which pressure we have to take? Either we have to take P1 or the P2. So that we have to make sure. And how much change in volume is taken place. We cannot directly apply the equation of PdV. We may not get the correct result. But if we draw the PV diagram or TV diagram, we can get the correct work which is produced by this piston and cylinder arrangement when we have used the R22 refrigerant. Now we have to find out the work done, and this first we have to see the PV diagram, how these PV diagrams are working. So here we can see that 1 to 2. Okay, just I will draw a small piston cylinder arrangement here. And this you can see here that this is our piston and these are the stops here. These are the stops, and here we have the refrigerant. This is your system. This I am putting, and here you have the R22 is filled here, R22. So this is the state 1 and this is the state 2. So from here to here, initially this is the volume V1 and here is the volume V2. So V2 minus V1, it is a dV is equal to V2 minus V1. And here pressure is remain constant till it is coming here. So we have to take the same pressure here, and this volume change from here to here. So this is our work done. In this way we have to find out that how much work we have produced. So we need to draw a PV diagram which I have shown here. So just you can see that first case from 1 to 2 here. From 1 to 2 it is a constant pressure process. This is the V1 and this is the V2. So it is expansion of this gases and this will give a positive work. Work is produced by this system if volume is increasing. So it is from 1 to 2. But here is 150 kilopascal is constant. 1 to 2. But after touching this stops here, pressure will reach here. It is a P2. P2 is 164.7. 164.7 kPa. And here we have this much. So after reaching to 2 here, the pressure will keep on building till the time it reaches to 160.7, and this is happening at the constant value because now it is not moving. So next 2A and 2A to 2 is a final state. This is your final state. In this final state, your pressure is 164.7 kilopascal. So we have to see that how the work is done. So we need to draw a PV diagram which I have just now explained. Before you attempt any problem, PV diagram is must. Otherwise, the results will not come correct. Because you see that it is a P1, this is the P2. You may draw like this. This is not correct. If you draw like this, your results will be totally different. Then what you go with the process. Because you know that heat and the work, they are the process properties, not the point properties. So their del W is important, not the dW. So it is inexact differential. And if you go from here to here, it gives you exact differential, which we cannot use it. We have to use only del W, not dW. Okay, so here we can see by this diagram and we can write that the work done by this process, which I am from here to here is 150 kPa. Okay. So we know that work done W12 is equal to 1 to 2 PdV. So here we can write that 1 to 2A. First from here to here, it is a 1 to 2A plus 2A to 2. So here PdV plus 2A to 2 PdV. We can see here that 2A to 2, this process here is a constant volume process. So there is dV is equal to 0. So this dV is equal to 0. So we can write here that work done from 1 to 2 process is equal to 1 to 2 PdV, 1 to 2A PdV. So we can write for P, it is a dV, it is a total volume and divided by M. So here we can write as MP1 V2 minus V1. This V2 minus V1 are specific volume. Small letters are specific volume. The specific volume is a volume per unit mass. So if you write this mass, if you write this P1, here we have to use the P1 as 150 kilopascal, not 164.7 kilopascal. This we should not use. Only this process here to here is 150 kilopascal. So we have to use 150 kilopascal. That is why I want to say you have to make the PV diagram. Then only you can get the correct result and correct application. Otherwise, this you may write like this, straight line. So this I am going to explain below. So this you can see here that here mass we have already got. If you see this previous year, we have the, this you can see, we got the mass here, V1 by capital V1 by V1. So from here we will get the mass, and this mass we have to put this value here. We have to put here 150 kilopascal, and then V2 is given and V1 is given. So you will get 0.15 kilojoule, and this is the answer for your problem. So we should have one caution on that final pressure P1 doesn't matter, only P2. Final pressure P2 doesn't matter, only P1 needed to find the work. So if you draw a PV diagram like this, which is not correct, 1 to 2 like this, so you can write the work as this trapezoidum from here to here. This is the work done, which is not correct. The correct work done only this. This is your extra work, which you will get the result. That is not correct. So here 1 by 2 P1 plus P2 and V into V2 minus V1. So is not correct because 1 to 2A is a constant pressure and 2A to 2 is a constant volume, and in constant volume no work is done. So only constant pressure will provide the work. So that we have to take care and make sure that the work is performed as per the requirement. So I hope this problem is very much clear, and try to practice this problem. Very interesting problems are there. I am referring my reference one. If you see first one, all the problems are taken from this Senegal thermodynamics and engineering approach. I have taken from there. Now I will go for the next problem, the numerical number 3. So hope you have understood this problem, how to find out the pressure, how to find out to have the state point, minimum 2 properties are required. If you have the one property, try to find out the another property by the steam table or by some ideal gases. If it is air, nitrogen and all which follow the ideal gas equation, you can use the ideal gas equation. But for the vapors where the phase change materials are there, refrigerant, water vapors and all, we cannot use the ideal gas equation. So we have to take care that these things should not happen, and we should try to develop the ideas. So I welcome you all here for the numerical problem number 3. Very, very interesting here. Some new things have been added in this system. So 2 kilogram of water is contained in a piston cylinder as shown in the figure, with a massless piston loaded with a linear spring and the outside atmosphere. Initially, the spring force is 0 and P1 is equal to P0 is equal to 100 kilopascal with a volume of 0.3 meter cube. If the piston just hit the upper stop, the volume is 0.8 meter cube and the temperature is 600 degrees centigrade. Heat is now added until the pressure reaches to 1.2 megapascal. Find the final temperature, show the PV diagram, and find the work done during the process. So here we have to find out 3 things. First is the final temperature. What is the final temperature of this system? Then we have to draw the PV diagram, and then we have to find out the work done. As I have discussed earlier, to find out the work done, PV diagram is prerequisite. We must draw the PV diagram, then only we should go ahead to find out the work done. So before we go for the PV diagram, the first problem is that find the temperature of the find the final temperature of this system. So here we can see that in this we have the water. So you know that water is also phase change. So in this also we cannot use ideal gas equation. P1 V1 by T1 is equal to P2 V2 by T2 or M R T1. We cannot use that. So we need to use in this steam table we have to use it. And I have discussed in my previous classes that how to find out the pressure, temperature, specific volume, entropy, enthalpy. All these things we can find out by the help of steam table. So here we have the 2 kilogram. H2 is how much? Here is 2 kg. And here is the system. This is the system and it is a closed system, control mass system. Mass will remain constant. So that is for any state, your mass will, if the piston is going from here to here, mass will same. Mass will not be transferred. So everywhere we discuss about the control mass system. So here the linear spring, just you can see, we are telling the linear spring because it is the forces F applied by this linear spring is equal to F is equal to Kx, where X is the displacement of this spring. So initially it is your piston is here and here 2 kg. Initially the spring force is 0. So here F spring or Kx is equal to 0, means it is not touching. First case. And P1 is equal to P0 is equal to 100 kilopascal. So here the atmospheric pressure. This P1 is equal to P0 is equal to 100 kilopascal. With the volume is given V is equal to 0.2 meter cube. This is the initial condition. If the piston just hit, so now if you give some heat, it is expanding and this piston has reached here. It is hit. So if it is hitting means the pressure will change. This is the indication. So it is hitting or not. How we will ensure? We will calculate the pressure at the second stage, and if we find that this pressure is more than the initial pressure, then it is a case of hitting. So if the piston hits the upper stop, the volume is 0.8 meter cube and the temperature is 600 degrees centigrade. Heat is now added until the pressure reaches to 1.2 megapascal. Find the final temperature. So this we are going to handle, and really it is very interesting problem, and this will give lot of application in the real scene. Whenever you are using some spring damper or anything in your mechanical devices, hydraulic systems, or any piston cylinder arrangement, we can calculate how much pressure and how much temperature and how much thermal properties will change. So that is the objective of this type of, all the problems which I am going to discuss are depend upon the real application. It is not just only for numerical solution issues. So here we have to go for this solution and schematic of the problem, which this you can see, this is these are the stops. These are the stops. This is the cylinder. This is the piston. So if you see here that I'm hatching here because pistons. Okay, and now if you see, this is the spring, and here is P naught is the atmospheric pressure here, and here is, this is the your system, and in the system you have the water. So we have to first see that what type of system is it, whether this we can use for our steam table, or we should go for the direct calculation by the help of gas equation or the ideal gas equation, whether it is possible or not. So from here itself, the system is a water, and water we cannot use because it is a phase changing as per the pressure and the temperature, phase will change. We cannot use the ideal gas equation. So that is sure. First we have to decide that whether it is, the system is ideal gas or not. So the water and all refrigerant we cannot take as a ideal gas system. So now first we have to see the force balances, how the forces are balanced. So we have to draw the free body diagram. Here, this you can see here that this is our piston. In this piston, if you see here, this is here pressure from this bottom side. So here it is pressure into area of this piston. If you see the weight of this mg of piston, weight of the piston, mass of the piston, mg into P, and the atmospheric pressure is exerted. This is, here is a P naught into A. And then spring. Spring is also acting towards the downwards. It is pressing downwards because it will try to go up. Spring force will be in this direction. So I have shown here Kx. So we will, for the equilibrium, this PA from the bottom side and is equal to summation of the top side. So this PA is equal to mgp into G plus P naught A plus Kx, where Kx is a spring force. As it is a massless, in the problem it is given as a massless, so this will be 0. So here we will get PA is equal to P naught A plus Kx. So this P is equal to P naught plus Kx by A when x is equal to 0. Condition is given. Okay, condition is given when it is just touching. P1 is equal to P naught. This condition is, if you make x is equal to 0, you will get P is equal to P naught. And this is also given in our problem also. This issue is given. Now we will see that what the items are, what the features of this systems are given, and how we can go ahead to solve this problem. So this we can see that at state 1, P1 is given 100 kilopascal, V1 is equal to 0.1 meter cube per kg. Actually this V1 is given as a 0.2 meter cube, but the mass of this is given as a 2. So this V1 is equal to 0.2 by 2, and this will come 0.1 meter cube. So this is mentioned here. So this water mass is given 2 kg. Total volume is 0.3 meter cube. So specific volume. This is called specific volume. All specific volume should be in small letter. This V1 is equal to 0.2 by 2. You will get 0.1 meter cube per kg. The system is a water, so it's two-phase system. We cannot use ideal gas equation, so need water table to solve these problems. So anywhere if you find that there are some different shapes or different phases of the material, we should always use the steam table or refrigerant table as and when it is required. So we have got the P1 and V1, the one state we have got for state 1. Now for state 2, given V2, that is here V2 is equal to given 0.8 meter cube. So small V2 is equal to 0.8 into divided by 2, 0.5 meter cube per kg. So here this is specific volume is equal to 0.8 by 2, 0.4 meter cube per kg, and T2 is given 600 degrees centigrade. So second condition is also given. For a simple compressible pure substance, two properties are needed to locate the state postulates. So for any this simple compressible pure substances, minimum two properties are required to postulate its position. So here the P2, which is also the hypothetical state, we can get. So here P is equal to 1 megapascal. So this P is equal to P naught plus Kx by A. So here P naught plus K, X we can write delta V by A square. So we can write here P naught plus K, delta V means V minus V naught by A square. So this is the equation, the relation between P and P naught. So this P will be always more than this much. This is more than this atmospheric pressure. Here we should have the note that here P is in linear relation with the volume V. So here this you can see P and V, they have the linear relation with volume V. So in PV diagram will be a straight line. By doing this, without a spring constant K value, we can get the pressure. That is the specialty. We don't need this K. Without this, we can get this value, total value, and how we are getting that I will be explaining in subsequent paragraphs. So without spring constant K value, we can get the pressure. The actual state point is due to the added heat. So now the pressure is P2 is given 1.2 megapascal. This is the actual state. System is started with 100 kilopascal and the fixed pressure is given and the final pressure is given by 1.2 megapascal. So the hypothetical point is correct because it is in between, and this point is now real as proved by the values. So this we can see that the P hypothetical is given 1 megapascal. So it is from 100 kilopascal to 1 megapascal, but the final is 1.2 megapascal. So this hypothetical which we have assumed is really correct and it is hitting the system. So we have to see that state 3. In this, P3 is given 1.2 megapascal. V3 is equal to V2, because as and when it is touching this thing, the volume will be constant, that is the 0.8 meter cube. Work done is equal to 1 to 3. So work done is equal to 1 to 2 PdV, then integration of 2 to 3 PdV. But here 2 to 3 volume is constant, because just I will write here. Okay, this we can see here that how these things are happening. So as and when this piston is moving upward, it is hitting here. After hitting here, volume will not change. So here this 2 and 3, no change of volume. No change of volume is taken place. So we can write here that P1 to 2 PdV plus 2 to 3 PdV. This dV is equal to 0. V constant. Okay, so area of the trapezoidum here 1 to 2 under this plus 2 to 3 PdV. But here dV is equal to 0 for 2, 3. So here we will get that area of the half P1 plus P2. P1 here, and this is the P2. If you see, this is the P1 and this is the P2 and this is the P3. P3 is not taking part in work done, because volume is not changing here. So here we can see that this is half P1 plus P2 into V2. This is the V2 minus V1 plus 0, because this work is 0 here. So 1 by 2 P1, it is a 10. P2 is equal to 1 plus 0.8 to 0.2. So you will get here 1 by 2 into 11 into 0.6. So you will get here 0.3 and you will get 330 kilojoule. 330 kilojoule. So in this way you will get the answer for this problem. So state 3 given P3 is equal to 1.2 megapascal, V2 is equal to V3 is equal to 0.3 meter cube per kg. For the water table, by this P3 is given, V3 is given, so we can find out the third, and this is coming 770 degree centigrade. So this is the answer for this. So the final temperature we got, final temperature T3 is equal to 770 degree centigrade. This is the answer for the final. This is the answer for your PV diagram, and this is the answer for the work done. This is the work done by this system. So in this way we can find out any type of work, how the work is extracted, how the work is utilized, and how the pistons and systems are working to find out the work of a given system. So in the next topic I will discuss about the first law of thermodynamics, energy and work, internal energy as a property. So please be tuned. These lectures, the first law of thermodynamics is very, very important. It is just like a conservation of the energy for the thermodynamic process, and how the work and heat can be transmitted from the transform from one form of another, and how internal energy and the work is taking place, and a new property will be discussed, that is called the internal energy as a property. These are my references. I am referring for all numericals and other things. Eunice Sengel and Michael A. Balls, Thermodynamics and Engineering Approach, Tata McGraw-Hill's 7th edition 2011. Also, I am referring this YouTube videos, and this may be useful for your future references. You can go on this. Any questions, you are welcome to ask. My email is ydwibedi@gmail.com. I will also request to like and subscribe this channel, and if any comment, please do comment in my comment box of this YouTube channel. Thank you very much for the joining, and hope we will be meeting again for my next lecture, that is the first law of thermodynamics, very soon. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.